So we're now going to start to think about how we think about rolling motion from a sort of qualitative perspective with regard to breaking motion down into translation and rotation. So qualitatively, if you think about what rolling motion consists of rotation about the center of mass plus a velocity that is a translational velocity of the center of mass. So this is my rotational part, and this is what my translational part looks like. And furthermore, it's the case that we know that due to the constraint, the angular velocity of the object is simply the linear velocity divided by the radius with a negative sign, or vice versa, right? The linear velocity is negative omega times r. So there's actually a relationship between how fast this rotation is and how fast this translation is. In fact, this rotation is just fast enough that the ball in rolling doesn't slip past the surface. We talked about that as a constraint. So what does this actually mean with regard to the motion of different points on the object? Well, let's think about some different points that are on the object. And first I want to think about a point that's right here on the right-hand side of the object. So if I think about the rotational part of that motion, the rotational part of that motion is the object is that point is moving down, right? And if I ask the question, how fast is that point moving down? Well, the velocity there is simply going to be omega. So the downwards velocity is going to be omega times r in the j hat direction. Omega is going to be a negative quantity since the velocity is positive, so it is going to indeed be omega times r in the j hat direction. So that's what my downwards velocity is. I'm also going to add to that my center of mass velocity. My center of mass velocity, of course, is going to be minus omega times r in the I hat direction, which will be a positive number. So this point on the object will actually be moving in that direction with a 45 degrees with a total velocity that's actually square root of 2 times omega times r. By the same token, if I think about a point on the left-hand side of the object, what's going to be happening? Well, that point has a velocity due to rotation that is up, that a value of minus omega times r times j hat, and a velocity that is the center of mass component. So this point has a velocity that looks like that, 45 degrees, square root of 2 times omega times r. This point on the top of the object, right, has a velocity that's the rotational velocity. The rotational velocity of that point on the top of the object is minus omega times r in the I hat direction, or plus absolute value of omega times r I hat. So there's my translational component, my rotational component. Right? This is rotational, that's translational, that's rotational, that's translational. So I've got a rotational component that's forward plus a translational component that's forward. And then finally, so the total velocity of this point on top is actually 2 or minus 2 times omega times r in the I hat direction. And then finally on the bottom, I have a velocity that's due to rotation that's omega times r in the I hat direction, and a velocity that's due to translation that's minus omega times r in the I hat direction, so the velocity on the bottom is 0. So if I actually draw this wheel that's rolling, the top of the wheel has a velocity that's twice the velocity of the center of mass. The center of the wheel obviously is moving at the velocity of the center of mass. The bottom of the wheel has 0 velocity. This point on the right-hand side has a velocity that's square root of 2 times the center of mass down, and this point here on the left-hand side has a velocity that's square root of 2 times the velocity of the center of mass up and to the right. So it's a pretty strange motion that the different points on the wheel have if you think about what that sort of effectively means, but in fact all it is due to is this combination of rotational motion and translational motion. Now, of course, we could get more mathematically rigorous about this and say, okay, well, the velocity of a point on the wheel, let's say a point on the wheel at the angle theta, right? So we're interested in, say, this point that's at the angle theta, right? Well, if I think about what that must be, that's the velocity of the center of mass, right? Plus the velocity about the center of mass. The velocity of the center of mass is simply the value minus omega times r in the I hat direction. The velocity about the center of mass is going to be theta dot times r times theta hat, or the second term. So if I'm going to write out both terms, sorry. So minus omega times r times I hat plus omega times r times theta hat, right? So in the case with that, I'm at theta equals pi over 2, right? So if I think about different values of theta, when theta is pi over 2, well, I've got minus omega times r in the I hat direction, which will be forward since omega is negative, plus omega times r in the theta hat direction. Well, theta hat is in this case in the negative I hat direction. So these two terms, so I'm going to get a negative here, I get a negative there, I get minus 2 times omega times r in the I hat direction, right? If I think about this point here, this term is going to be forward, this term, theta hat at this point, is in that direction, so this term will cancel it. Here I'm going to get the same behavior I got before, and so on. So you can sort of see where these different terms come from if you actually do the math using what you know about polar coordinates, or a combination of both polar and translational coordinates, and what is sort of the natural coordinate system for this case.